Welcome to lesson 3.7, size transformations. So in this case, a transformation means a change. So the title, size transformations, we are looking at how we change the size of different figures or shapes. So our first example, triangle ABC has the vertices A at 1, 0, B at 1, 5, and C at -3, 0. So the first thing you want to do is graph that original triangle of ABC. So 1, 0, 1, 5, -3, 0, connect your points, and you have triangle ABC. Then it says, suppose we want to enlarge the triangle by 3 times. So enlarge meaning getting larger 3 times. The way that we do this size transformation is you multiply each ordered pair by 3, and then you would graph that final image. So in this case, we already graphed the pre-image, ABC. So to get the coordinates for our image, which would be A prime, B prime, C prime, we just multiply each ordered pair, so the X and the Y value, by the transformation number, so 3 times larger. So 1, 0, both multiplied by 3 would give me 3, 0. For B, 1, 5, both multiplied by 3 would give me 3, 15. And for C, -3, 0, multiply both by 3, is a -9, 0. So then you plot those 3 coordinates, A prime, B prime, C prime, connect them, and you have your similar triangle that is 3 times larger than the original pre-image. So if we were shrinking, we would be multiplying by something less than 1. So if it says it was being shrunk to half the size, you would then just multiply each of these by 1/2. So a transformation, as I said, can be broken down to this idea. It's the correspondence between 2 sets of points, A and B, such that each point in set A corresponds exactly to 1 point in set B. And then each point in set B corresponds to 1 in set A. So our set A in the first example would be our 3 original points. Our set B after the transformation would be the 3 new points. Each has a 1-to-1 relationship. Now, sometimes you'll hear transformations called mapping. And it's said that a transformation maps a pre-image onto an image. So that's where that term mapping comes from. So if you hear mapping, it has to deal with size transformations. So in this case, the correspondence can be described by the rule x comma y equals or becomes 3x comma 3y. We call this a size change or a size transformation with a magnitude of 3. So in rotations, the magnitude was degrees, positive or negative, based on the direction. In transformations, the magnitude is the size that we're changing by. So our scale 3 times bigger would mean a magnitude of 3. If we were shrinking to half the size, our magnitude would be 1/2. So the way that we write that is using this symbol denoted by S, capital S, lowercase k. So what that means is that the lowercase k is the magnitude, what we're changing by. And the S simply stands for size transformation. So when k is not equal to 0, the transformation in which xy would become kx comma ky is the size change or transformation, the magnitude k, and the center point, it's centered around 0, 0. So in this case, both of these graphs were based around the origin of 0, 0. So that's why we could just multiply each by our magnitude. So our the donation here of S sub k, capital S just means size change. The k is the magnitude. So how we apply that is here in example 1. If we knew W was at the coordinates 6, negative 24, and W was going along with the size change of a magnitude of 2/3 W. So this notation means size change 2/3 of W. So we're just going to take the X and Y values, multiply each by 2/3, and our new coordinates for W prime after the change would be 4, negative 16. Or in example 2, it says, in the figure of the activity, show that AB and A prime B prime are parallel. So our activity up here, they want us to show that line AB and A prime B prime are parallel. So what that means is I need to show they have the same slope. So what we can do is take change in y over change in x. In that case, I'm going to use, instead of A and B up above, I'm just going to use W and W prime from this part here. So if W was originally at 6, negative 24, and W prime was at 4, negative 16. If both of these are based around 0, 0, I could prove that they have the same slope. So in other words, change in y, negative 24 minus 0, over change in x, 6 minus 0, would mean that that has a slope magnitude a slope m of negative 4. The negative 16 minus 0 and the 4 minus 0, so change in y over change in x, also gives me a slope of negative 4. Or if I look up here, change in AB, so from B to A, would be 5 minus 0 over 1 minus 1. It's a vertical line, so it's undefined. Same with this one, A prime, B prime. It's also undefined or a vertical line, so they are parallel. So no matter what we're looking at is this parallel property, which is part of our size transformation theorem 1, which says under any size change, the line through two preimage points is always going to remain parallel to a line through those image points. So A or BC will always remain parallel to B prime, C prime. AB will always remain parallel to A prime, B prime. So our parallelism is still true, meaning it's preserved. So then we have collinearity. Collinearity is preserved as part of theorem 2, which says under size change, the images of collinear points are still collinear. Collinearity being preserved means if in the original preimage, B and C are collinear, in our final image, they will also still be collinear. So collinearity is preserved. And then our final theorem here, theorem 3, is the angle measure is preserved. So under a size change, an angle of the image will have the same measure of the angle of the preimage. So angle BCA down here will have the same angle measure as B prime, C prime, A prime. That angle measure is preserved under the size transformation, so it doesn't change. So 3 things that are preserved: parallelism is preserved, collinearity is preserved, and angle measure is preserved.